experimenters. I'm Seth Law, the man behind the camera with the exceptional handwriting, as you see above. Today is all about capacitors, so let's get started. I want to bring up the formula for the series capacitors and the parallel capacitors for two reasons. The first reason is a very, very common mistake. A very common mistake of forgetting this -1 when you calculate the series capacitors. Don't let that be you. Another common mistake is to confuse the series formula with capacitors for the parallel formula of resistors, and to confuse the parallel formula for capacitors with the series formula for resistors. Don't let that be you. All right, we are interested in an RC circuit, a resistor and a capacitor, and when we look at it, when it's charging, we have an EMF. So from the magic of Kirchhoff's laws and calculus, we derive this equation for the voltage drop across the capacitor. And I want to point out something while we're here. We have e to the minus t over RC, which tells us something that's interesting. That if we take R times C, resistance times capacitance, we should get units of time. That's intriguing. All right, so let's see what this will look like. Let's see, at time 0, this should be e to the 0, which is 1, 1 minus 1, which is 0, so we start at 0. Let's see, as time gets really, really large and approaches infinity, this would be e to the minus infinity, 1 over really, really large number. That's 0. That's 0, so this would be V naught times 1, which is just V naught. So it asymptotically approaches V naught. So let's see here. Suppose V naught there. And then it will look like this. Aha. There we are. All right, so then suppose that we turn the battery off, we take away the EMF, and we get this circuit. In other words, the capacitor is now discharging. Once again, through the magic of Kirchhoff's law and calculus, we get this. The classic exponential decay formula. All right, let's see what this looks like. At time 0, this is e to the 0, which is 1, start at V naught. As time approaches infinity, this will be e to the minus infinity, which will go to 0. It exponentially decays, or it asymptotically approaches 0. So it looks like this. Aha. All right. So now, we're going to put a special kind of wave through our RC circuit, a square wave. In other words, it's going to be a series of voltages that are on, off. The on will correspond to this circuit when there's an EMF, and the off will correspond to this one where the EMF is turned off. So if we put these two together, it should look like this. The capacitor will be charging, discharging. All right. So we're going to focus in on one piece. We're going to zoom in on a discharging piece like this. We're going to set our V naught to 8 volts. And then we're going to make sure that we're in the scale of volts versus milliseconds. And we're going to be able to tell. Let's see. I want to find out how many milliseconds it takes to decay 1 volt. In other words, at 7 volts, I can then read the time in milliseconds. And then say I want to go down the half-life. I can see how much it decays at 4 volts. And I can find the time it takes to do that. All right. This is screaming for us to do a linear regression. So we need to linearize our decay formula. Okay, we know how to do this. Divide both sides by V naught, take the natural log of both sides, do some arithmetic, and we'll get this. This is linearized. This is linear. So in other words, this is the y, this is the m slope, and then this is the x. Alright, so when we graph it, on the ordinate, we'll have the natural log of v naught over c versus on the abscissa, time. And then the slope of this line you'll get should equal 1 over rc. And if we know r, we know the slope, we can find our capacitance. We can calculate our capacitance 1 over r times slope. I'm going to just point out something about the units here. Let's see, if time is in milliseconds, then slope will have units of 1 over milliseconds. And if r is in kilo ohms, this means that the capacitance will be in microfarads. All right. Last bit of theory is to find an expression for the half-life. So in other words, when half of V naught decays, can we find an expression for the time? And if we know the time, can we find the capacitance from it? So let's see. So from some arithmetic, we find this. The capacitance equals the half-life divided by r natural log of 2. So I want to point out something while we're here. There's a direct, look at this, the direct relationship between the capacitance and then the half-life. So suppose we had two equivalent capacitors in parallel. Then the capacitance would double, which means the half-life would double. And suppose we had two equivalent capacitors in series, the capacitance would halve, which means the half-life would halve. Okay, let's go. Okay, here's our circuit board of the day. We have our resistor and our two capacitors, and you can even read on the yellow capacitors that it's around 0.1 microfarads plus or minus 5%. But let's directly measure everything. All right. So with our Agilent 34405A, I'm going to first measure the resistor, press the omega to find resistance, and here we go. Put this across the resistor, and there we have around a little bit less than 35 kilo ohms is a large resistor. Okay, great. So now we're going to measure the capacitance. That button is right underneath the resistance. In other words, underneath the omega is the capacitance button. All right, and then put these across one capacitor. All right, so it's around 0.101 microfarads. You can get another piece of data here. There'll be now 4 pieces of data, but notice that the scale changed to nanofarads. So if you're going to read this in microfarads, this would be 0.1015 microfarads. All right, be careful of that. And then do the same with the other capacitor. And you can see they're around the same. All right.